before doing that, let me show another intuition of what is the problem here. So here you see the RNN representation, but instead of using the usual color, the green, purple, and blue, I'm using this black and white. And the reason is that, well, you can see that there is the input, the internal state, also called hidden layer, and the output. So it's the usual RNN. But here you see I'm trying to show with the color how much the information is fading away. So let's say that I have an information at time step 0 here. This information is, well, is present at time step 0, but you see that it starts to fade the more we go far away from that moment. And this is basically what we saw before in the long-term dependency example. So you see that the problem is that the RNN seems to be not so good in keeping the information. And obviously, if I need this information many steps after this step 0, it will not be there for me. So one intuition to solve this problem is actually to use, to try to better control the flow of information. So instead of having information going all over the RNN, I can try to use this idea of gating that is controlling when the information is going. So a gate is basically just one operation that is, a gate can be open or closed. When it's closed, it means that the information is not passing. When it's open, it means that the information is completely passing. And actually, I can have any value in between these 0 and 1 to model how much information should pass. And you see that now in this example, with the gating, I'm controlling the information, and now it can stay alive for a longer term. In particular, longer time. You can see that when we have a circle, that means that the gate is open, so the information is flowing. When we have a dash, it means that the information cannot flow, so it cannot go there. And again, so here it's interesting to see that we have a gate between the input and the internal state, which we will call the input gate because it's controlling how much information I will take from the input. We have a gate here between one internal state and the next one, which we will call the forget gate because it's telling us how much information should go to the next internal state. And we have one gate in output, which is called the output gate, because it's basically controlling how much information should go to the output. And this has been implemented in this architecture called long short-term memory, also LSTM. So for now, let's ignore the equation. Let's mention the two key points of this architecture. First one, there is a memory cell. So in the previous RNN that you have seen, the TAN H1, if you remember, there was the internal state, which we called H, which is still here. You see that the internal state is allowing the information to flow. But now, we also have this memory cell, which I called C. And the intuition is that the memory cell is hopefully learning to allow the information to flow for many steps so that it can be available far away when I need it. And we will see how this will happen. And the other intuition is the gate mechanism, which is the intuition we mentioned before. So basically, I have three gates. This one that I mentioned before, so the input gate, forget gate, output gate. And they will control the flow of information somehow, which we will see in the next slide. So let's go in detail. So first thing we mentioned, the memory cell. So the memory cell is this part here. And just to get an intuition, you can see that on the memory cell, there are few operations that are happening compared to what happened to the internal state. And this is an intuition of why the information can flow more easily on this particular lane compared to the internal state that we had before. In order to decide which information should go to the memory cell and which information we should use for the output, we use the gates. In particular, here we have the forget gate, which is basically telling the memory cell which information should be forgotten. And the idea is that information that are not interesting anymore, we will delete them, so we make space for new information. The forget gate is governed by this equation here, and you see it's somehow similar to the equation that we saw before for the RNN. So it's the usual a combination of the input and the previous internal state with some parameters. The difference is the nonlinearity. So we don't use anymore the tanh. We use this sigmoid. And the reason is that the sigmoid is very convenient here. Sigmoid is defined, well, it's this one here in the image. The output of this sigmoid is from 0 to 1. So it's very convenient to represent a gate, because we said that the gate is basically a door that can be completely open, which would be 1, completely closed, 0, or any way in between, trying to decide how much information should flow. So we will always use the sigmoid for the gates. So the forget gate is trying to tell the memory cell which information to remove, and the next step is tell the memory cell which information to add. And this is done with the input gate, which is, you see, it is exactly the same equation. What it changes are the parameters, they have a different index, and that's to make clear that we use a different set of parameters for every gate, so they have full flexibility there. Okay, so the input gates will tell us how much information I want to add, and this other equation here, the candidate value, will tell us which information I want to add. So by combining the two together, I know which information I want to put in the memory cell, which is indeed this equation here. So basically, the memory cell is a function of, so you see that it has some information that comes from the past, which is multiplied by the forget gate, so that I can decide how much information I want to keep. And there is this new information, which is GT, which is multiplied by the input gate. So I can decide how much new information I want to add. So there is full flexibility there for the LSTM to decide what to do. Last gate is the output gate, because we, at this point, we updated the memory cell, but we still have to produce an output. So we still have to update the internal state. And this is done with the output gate, which is the usual gate equation, with this equation here. So the internal state is a function of the output gate, which multiply this tanh and the memory cell CT, applied to the memory cell CT. So at this point, this architecture is, we have seen this architecture, so it's somehow complex. The LSTM indeed has many, many pieces, but again, the two intuitions are the important part. So the introduction of this gate mechanism to control the flow of information, and the memory cell, which hopefully is it is a lane that is allowing the information to flow more easily. And there is the GRU, but I will just give you the intuition. The GRU performs very similar to the LSTM in practice. It's a similar idea. The difference is that we don't have the memory cell anymore. We just have the gating mechanism. So I will not go into details. Maybe one thing to say, given you have less equations in the GRU, there is less computation to do. So you may consider using a GRU, which, by the way, is a gated recurrent unit. You may consider to use the GRU if you have latency problem in your task.